Hello, everybody. So this is the lecture looking at the patterns of biological diversity, the first one of that set. So when I think about it from a community ecology perspective, we can ask the question, why do different sprouts on Earth have different numbers of species? Now, if you know anything, somewhere around the equator has the most species, whether we're looking at, North America versus South America, or, just within a continent around the equator has the most species. Now, different places along the equator have different levels of species richness, yes, but a lot of this chapter is kind of looking at why do different spots have different numbers of species, and what we're going to spend some time looking at is first just kind of like defining how we determine that, and that's what this lecture kind of looks at. So kind of throughout this unit, we'll be looking at diversity at different scales. So from really small localized scales up to the global scale. So let's think about what diversity means, right? So we have this idea of, in culture, diversity means a bunch of different opinions or something, right? But with biological diversity, what we're talking about, at least in community ecology, is species diversity. You can have things like genetic diversity within a population of a single species, but we're talking in community ecology species diversity. So how many different species you have in a community. One thing I should define though is that the word assemblage is I will oftentimes use that, and what that's just really referring to is at a specific point in time what organisms we have in a specific community. Okay, so the most simple, easy way to define species diversity is species richness. Okay, the number of different species. So if we look over, let me get this work in here. If we look in community 1, right, we have, let's see, 1, 2, 3, 4, I'm missing one, 4 different species, right? And community 2 also has those same species. So right here, right? There's 2, 3, and 4. So community 1 has a species richness of 4. Community 2 has a species richness of 4. But there's another aspect to diversity, and that is relative abundance. So even though species richness here is both 4, there's a huge difference in relative abundance. And one other way to think of that is the evenness. So community 2 here is not very even. It's dominated by one species, whereas community 1 is very even, right? There's 1, 2, 3, 4, 4 trees of each species there. But evenness is a little tricky to get at, and how to actually do that can be or to explain that can be a little hard. So we use something called diversity indices. Okay, so we can quantitatively express this evenness side of it. And what it does, it allows us to do statistics and look at these numbers and compare things relatively easily. So species richness is really good. It's super easy to understand, right? Number of species here. So look at these 3 little communities. Think of different colors as different species. So we know that top box has higher species richness than the lower box, right? It's also more even than that lower box. But the bad thing about species richness is that the species are equally weighted. Okay, so if you look over here, let's see, we've got right here a purple, right here a purple, Okay, looks like 3 examples. Okay, so if you look at all the different colors, they've got red, gray, green, purple, and pink. Pinks. Okay, so 5 different species here. So species richness here is 5, right? But what that does then is it equates that red to that purple, which is really not fair to do because we know that there's, I mean, unless those purple things are elephants or something, they're not going to have a huge impact on the community. Whereas obviously in this community, the reds are probably going to have a bigger impact. So species richness is okay, but it has that equal weighting problem. So how do we get around this? Well, we can use different indices. Probably the most common index is the Shannon index. Okay. Um, what this is actually derived from is from determining entropy in a string of text. So um, basically think about the species as letters in a string of text, and it measures how uncertain it is to pick a letter, or I should say, think of it, this community has low uncertainty. What is the probability that you will pick a red here? Well, it's pretty high, so we have low uncertainty. We're pretty certain that we're going to pick a red from this community. But what about this one? How certain are we of knowing what the next color that we pick out of it? So if this is a jar of jelly beans and we're going to pull out a color, pull out a species, are we going to know what species that is? And the answer is no. So we have high uncertainty. So how do we do this? This equation's a little confusing, and it uses summation index, which is always kind of a pain in the butt. One thing I should have probably had on the other side is these things here, the Shannon Weaver and the Shannon Wiener. Back like this Shannon index is actually really old. We've used it for a really, really long time. And there was a misprint, a typo in one of the articles where it was found, and for a long time it was called the Shannon Weaver, and then it changed to the Shannon Wiener. Honestly, I don't even remember which one is right at this point, which one's the typo, but let's just call it the Shannon index, and then that's kind of what people are moving to these days. But a lot of publications will have either Weaver or Wiener. Now, if you look at this this equation over here, what we have is the Shannon index is just defined H. Why it's H, I'm not sure. Doesn't matter. But what we're doing is we're summing up from 1 to K, K meaning is essentially the species richness here, where we take the PI, which is the proportion. Okay, so I should write proportion in here. Okay. Oh, forgot. Wrote it right up there. PI is the proportion of total individuals that are in the ith species. So now that ith species just refers to this summation notation. Just bear with me for a minute. So what we do is we take these proportions. So let's say we have, this is our community here of, super realistic organisms. And yes, Big Feet is plural of Bigfoot. Anyway, we have 42 individuals in this mythological community. 25 of them are Big Feet. Okay, so if you take 25 divided by 42, what you get is this 0.6. Okay, so that PI is the proportion of total individuals that are in this community. So 25 out of 42. Then you take the logarithm of that proportion. So if you know anything about logarithms, this ln This ln is the natural logarithm. So the logarithm base e. It's pretty commonly used logarithm. Doesn't really matter which one we use here, but we always, in ecology, always use the natural logarithm. And if you take a logarithm of a decimal, what you'll get is a negative number. Okay, so we get the logarithm of 0.6 equal to this negative 0.52. Okay, then if you take this p times the ln of p, you get here. So if you take 0.6 times 0.52, you get this 0.31, negative 0.31. Okay, and so this sum here, so this negative 0.31 is p log p for Bigfoot, right? Then what you do is this summation means you sum all of these up. So 0.31, 37, 14, 0.09, add all those up, and you get the answer of 0.91. Okay, now what this 0.91 means essentially is what is it doing is it's integrating the richness and the evenness. So the higher the Shannon number is, the more species rich it is, and the more even your community is, the higher that number will be. So realistically, this can range from 0 to or I should say, theoretically, this Shannon number can range from 0 to infinity if you have an infinite number of species in a community. But that doesn't make sense, right? So realistically, what we get is, in most biological communities, some sort of number between this 0.5 and 0.3. 1.5 to 3.5, sorry. So that's the Shannon index. And I want to move then to our next one, which is the Simpson's index. The Simpson's index really is looking at a dominance index, okay, where we're looking at, what is the dominance of the most abundant or most common species. And what it really is doing is looking at what's the probability of pulling two of the same color, so two of the same species. So if you have a jar of jelly beans full of all of these colors, right, what's the probability of pulling, think of it most simply, a red and then another red. But it's not that simple. It's what's the probability of pulling a red and a red, or a green and a green, or a basically all of these colors. Okay. Now, if we know from this this community, right, you've got a huge dominance of red here. So what's the probability of pulling two of the same color in a row? Well, it's actually higher in this example than this example, right? Because here if you pull up a purple, what's the probability of actually pulling another purple? And the answer is it's probably pretty low. You're probably going to get another color. And how you do this then is the Simpsons is abbreviated as lambda, the Greek letter lambda, but it's the sum of the proportion squared for all of them. So we've got our mythical community here where you've got, sorry, I don't know what's going on with my mouse here. You've got this 25 out. Remember that the total number is here 42. So you take 25 divided by 42, and you get 0.6, and then 0.6 times 0.6 just equals 0.35, and then you do that all the way down, and you add them up. And for this, mythical community here, the probability of pulling two of the same species is 0.46. Now, what we see is that more even assemblages actually have a lower Simpsons. Okay, so oftentimes what we see is this 1 minus lambda, because everybody likes to see that a higher number means more diverse. This would then make it so that it's better, more easily understandable. So if we look at Simpson's index, let's just look at that more even assemblages. So what we see here is we have a really lopsided assemblage here, where it's really dominated by big feet and chupacabras, and there's very few Jersey Devils and Hodeiks, right? But if you have a more even assemblage here, where they're all pretty much somewhere around 25 individuals, what we get then is, for our Simpson's number is 0.25 here. So here we have a higher probability of pulling two of the same species, meaning it is basically less diverse here, whereas here we get a lower number, meaning it is more diverse. Or maybe I shouldn't use the word diverse, I should use the word even. Now there's other forms to do it, this bias corrected form. You can use that, I guess, and all it is doing is taking, so this NI would refer to this 25, well, let's use this one, this 25 here. So it'd be, you'd put in a 25 times, oops, messed that up a little bit here. Let me see. Okay. So you would have this NI here being in this case 25, and then n minus 1, 24. So you take 25 times 24, and then you would take 22 times 21 and add all that up, or sorry, 25 times 24 divided by 40, in this case 96, 96 times 95, and you would add all those up, and when you do that for this example here, you get a slightly lower number. Either or works fine. I don't care which one you use in this course, as long as you define what you're going to be using. Honestly, the original form is just as good, pretty much, and it is much easier to calculate. So that's the Simpson's index. Let's go into then, if we want to compare two communities, how similar are two communities? Now, the Jacquard Similarity Index looks at that, and it uses only presence and absence data. So take two communities and see what percentage of the combined species pool is shared. Okay, so what do we mean by combined species pool? Well, imagine in community 1, you have species A, B, and C. And then in community 2, you have species C, D, and F, right? Now the combined species pool then is A through F, right? Then what's shared then is just the C, okay? So proportion of combined species pool that is shared, and it varies as a proportion from 0 to 1. So if you have 0, you have nothing in common. If you have 1, you have all the same species. So one way to, the notation here is using Jacquard's is J, right? So that makes it a little bit easier. but and then in the parentheses here, you would have comparing two communities. So in this example, it's comparing community A to community B. And what it is this notation is looking at the intersection divided by the union. Okay, what does that mean? So it's the number of species in common. So in this Venn diagram, the numerator here is looking right here, and then the denominator is basically this whole part. Okay, so in this case, it would be A through F. You know what? I can't believe I just did that. I'm doing this late at night. This should be an E. I'm very sorry. I think you know what I mean. Anyway, let's move on. So here's a little example of, let's just some made up data here looking at a tropical rainforest, okay, where we have a primary forest, a secondary forest, so a forest that's been cut down and regrown, and then a banana plantation. So which organisms do we see where, right? And now let's say we want to find out which two of these communities are most similar. And you know, it's really easy to see, you know, when we have really simple examples, you know, with only 5 species here. And if we were to have a third community, let's say number 3 here has A, B, and C, and let's say maybe it has species E. I don't know where C went, but okay. So if we ask, you know, well, actually, let's not have it have E, you know, or C. Sorry, bad example. Let's say it has community 3 has only species A and B. Well, it's easy to see that that is very similar. It's going to be more similar to community 1, right? But it's a lot harder when you have a whole lot of species here. And even here, just looking at the data, you might not be able to actually determine just with a quick look at it which community is most similar. So primary and secondary here share 8 of the 13 total species. So, you know, of these species here, there's 13 of them, and they share 8 of the 13. Primary and the banana then share only 3 of the 13 species. Secondary and banana then share 4 of 9. These, you know, these yellow ones right here, right? Now, you might be asking, well, why isn't this 13? And the answer is that the global species pool for the combined species pool does not include the puma, the jaguar, the forest rabbit here, or squirrel monkeys. Okay, so we've got 4 species here that are not in the combined species pool for secondary forest and banana plantation. And when we put all those numbers together, what do we get? Is that when we compare primary and secondary, we get essentially they share 62% of the species. Primary and banana share 23% of the species. Secondary and banana share 44% of their species. So what is this is saying? Basically, primary and secondary are most similar, but then actually, I should say, primary and secondary are most similar to each other. The banana and the secondary are then next most similar to each other, and primary and banana are farthest away from each other. Now, one way though, if let's go back to look at this, these tables here, right? It's kind of really hard to determine what's common and how many organisms are in this community. It's there's just the humans are not good at interpreting this much data um, all at once. So one way we can do that is with a rank abundance curve. Okay, now what a rank abundance curve does is what you do is on the x-axis you put the most common species here on the left at number 1, and then you plot their abundance. You can do proportional abundance here. You can do some sort of log transformation. Doesn't really matter. And then what you do is you find the second most common species and put it there, and the third most common species and put it, and so forth. And what you do is, you'll have it top high at the top left here as the most common, the single most common species, and bottom right is the least common species. And what we find, we can find species richness really quickly, because what that species richness then is just how far it goes on the x-axis. So if you look here, Centennial Brook has fewer species than Potash Brook, which has fewer species than Snipe Island Brook. Oops. And because this is log transformed here, right? So 0.001, 0.01, 0.1. If you were to plot these numbers out, in absolute numbers, what you'd find is this blue line would stay a lot more not so vertical, right? Whereas the black line here is pretty steep here. And what that means is the blue community has a relatively even community as opposed to the black community, which has a relatively uneven assemblage. So if you think about Shannon, what would you expect for the Shannon index here? You expect a higher number for the blue as opposed to the black. Now, how do you create these? So what we've got here is, again, our mythical community, where we have, what you do is you rank them in what's the most common. So we have the most big feet, so put a 1 here, right? Chupacabra, that's 2. Jersey Devil's 3. Obviously, this is a really easy example. And then you put the species rank down here, where, okay, 125 for the Bigfoot, right? So that is right here. 125. So this Bigfoot number comes right here. The Chupacabra number comes right there. And so forth. But what it does then is it allows you to really quickly integrate how the whole community with lots of different species is organized, and whether it's really even or whether it's not so even. And really, what you can do is you can extract a whole lot of numbers out here. And, just looking at these things, what do you think about urchin barrens versus kelp forests? Just think about it for a second. And hopefully what you'll be able to see is that kelp forests have more species, right? Because they're farther out on the x-axis, and because their lines are much not so steep, there's a much more even community in a kelp forest as opposed to an urchin barren, which this only has a couple species, 2 species here. This sample, or this community right here. So it allows us to really quickly figure out things about the community. All right, that's it. See you later.